Hello, my name is Zachary Hedges, and this is my Lab 3 submission on orbits. The purpose of part 1 of this lab was to find the mass of a black hole using the force of gravity on a star orbiting it. The goal of part 2 was to create a model of a spaceship orbiting around a planet and a moon in a figure 8, without the ship crashing. In part 1, the system was a star and a black hole. In part 2, the system was a ship, a moon, and a planet. There were no surroundings in either of them, as all of the aspects were in the system. The key physics principles are Newton's second law and the gravitational force. The key findings for this lab in part 1 was that the mass of the black hole was greater than the mass of the star, and in part 2 I found it difficult to create a figure 8 orbit, but it was possible to create an orbit in which the ship did not crash. Newton's second law states that force is equal to mass times acceleration. Using this, we're able to update position and velocity using the position and velocity update formulas. And then the gravitational force is present in both parts of this lab, as this force is what is responsible for creating orbits. So in part 1, where the star is orbiting a black hole, we set the initial conditions with the mass of the star and the time interval. We use the mass and velocity to find the momentum, the initial and final. And then so that we can calculate delta P. To calculate force, we divide delta P by delta T, and that results in our net force. To find the parallel component of force, we take the magnitude of the final momentum, and then subtract the magnitude of the initial momentum, and then divide that by delta T. We multiply that by the unit vector of the momentum to get the parallel component of force. Since Fnet parallel plus Fnet perpendicular is equal to Fnet, to find an Fnet perpendicular, we can subtract Fnet parallel from Fnet. To find the mass of a black hole, we can rearrange the gravitational force formula to solve for the mass. So from part 1, I found the mass of the black hole to be 1.3755 times 10 to the 34 kilograms. The green path is the star's orbit around the black hole. The purple arrow shows the parallel component of force, which points in the direction of motion. Blue is the perpendicular component, which towards the center of the turning circle, and the orange arrow is the net force, which points towards the black hole. Part 2, we were to find a ship's orbit where both the moon and planet were exacting a force on it. I set the initial speed of the ship to be 25,000 meters per second in the x direction and 29,000 meters per second in the y direction. I calculated the force of the planet on the moon using the gravity formula, and I did the same for the ship on the moon. So Fnet on the moon was equal to both of these forces added together. Then to find the forces on the ship, I found the force of the planet on the ship and added the force of the moon on the ship. The moon's position and velocity were only updated by the force of the planet on the moon, as this was the only force that impacted the orbit. The ship orbit was affected by both forces, which is why we use Fnet. Part 2 resulted in this orbit where the purple path shows the ship's trail. Its deviation from a normal orbit shows that there are multiple forces acting on it. Blue circle shows the moon's orbit around the planet. The loop ran for the intended duration, meaning the rocket did not crash. So a source of error in part 1 was that we approximated the black hole's mass by taking the average of all generated masses. In part 2, the initial velocity of the ship was an estimate obtained by guessing and checking. To answer the first question, the rate of change of momentum is equal to net force. Net force is the sum of the parallel and perpendicular components of force. Rate of change of momentum is not equal to a single component of force, but rather their sum. And to answer the second question, the force of the black hole on each of the other components of the system, and the subsequent equal and opposite force, would need to be modeled. The black hole would likely have dominant interactions as it has a greater mass, but this is also dependent on the distance from the other components. That concludes my lab.